So a very important example of quotient spaces are projective spaces, and this is based on these were invented by Cayley, actually the projective plane, and it's a really beautiful and brilliant idea. The goal was to complete the plane. That is the usual Euclidean affine plane. The point is that when we pass from real numbers to complex numbers, then the degree, instead of being an upper bound for number of roots, is exactly the number of roots up to multiplicity. However, in geometry you don't quite get this, because if I take a pair of parallel lines, if I take a pair of distinct lines, they could intersect in either 0 or 1 point, as if the degree only gave you an upper bound on intersection. And Cayley had an idea that you could complete things so that you would get exactly the correct number always if you count with multiplicity. And the idea was based on the following. So suppose we take, let's draw things with lines. Suppose I take, so here are my axes, and we want to look at the plane. But instead of looking at the plane through the origin, suppose we put the plane at some other point through 0, 0, 0, 1. Okay. So this is the plane we are looking at. It goes on to infinity, of course, in all directions. So let me do that part a little better. So we have a plane, and then we have a plane here. This goes on. So this is the point here, which is not with a line. This is the point which is 0, 0, 1. So we look at the plane through 0, 0, 1, and let's take a point on it. Okay, I'll take it here for simplicity of pictures because my pictures are so terrible. You see that given a point and a line and this, there is a unique line through the origin passing to this point. So if you put the plane at a little height, and then what happens is that the points on the plane correspond to lines through the origin. Not quite, there are extra lines through the origin, but each point gives you a line through the origin, and different points give you different lines through the origin. And what about a line here? Suppose we have a line in this plane. Okay, so we have a line like this. Okay, again I've drawn it through axis just so it becomes somewhat visible. Well, then you see that all these things give you a plane through the origin. A line gives you a so that is the dictionary that you get. You get an upgrade, so complete the plane. So the idea is that we look at the plane as points. So consider, or rather, let me say embed. Let me, for definiteness, say R2 in R3, though you would usually take an algebraically closed field like C2 in C3, and this will be more general as well. We'll generalize to other dimensions. Embed R2 in R3 by, we'll take XY maps to XY1. Okay, then points in R2, I won't quite say correspond to, they give lines through the origin 0, 0, 0 in R3, and lines in R2 give you planes through the origin. Again in R3. What about the converse? Well, I deliberately said both these because the converse, because at the level of planes, planes through the origin need not give you a line. They give you a line with one exception, which is the horizontal XY0 plane. Okay, and that, so lines in R2 are supposed to be planes through 0, 0, 0, but we have one extra plane. We'll regard that as an extra line at infinity. Okay, so these are so we have consisting of points at infinity. So you can think directly that if two lines are parallel, you treat them as equivalent, and equivalence classes of such lines give you undirected lines, watch out, will give you infinity points. Okay, so it's not really a direction because the direction and its opposite are the same. But roughly speaking, these are directions. So line at infinity consisting of points, and now distinct lines. Lines here means planes through origin. Oh, always intersect in a point. And in exactly one point, okay, as long as they're distinct lines. So they intersect in 2 points, they're equal to each other. This means that the many cases of Euclidean geometry get collapsed, and more usefully you get a much greater symmetry, because intersecting lines and parallel lines are not different anymore, and greater symmetry helps one study these much better. And Cayley's insight actually works very well, that this really completes things, in that if you are looking at two curves given by polynomials, then Bezout's theorem will tell you that counted with multiplicity, the number of intersection points is actually dependent only on the degree. It's given by the formula with degree and without any conditions. So points at infinity. So this really is complete in a nice way. So this was a background from a geometric point of view. What about the topology? What is this space really? Okay, now I might as well construct Rpn minus 1, or instead of just Rp2, instead of just the projective plane. So topology is that Rp n minus 1 is the following. We look at Rn minus, well, it's n minus 1, you'll see why. N is 3 here, so we're going to construct two-dimensional plane. So it's Rn minus the origin by equivalence, where tilde is being, so they're not origin, where I can as well write it in an explicit form. There's not an equivalence relation generated by, it's actually equal to. So xn, this is equivalent to, let's say, y1, yn, if there exists alpha in r minus 0, such that, well, y1, yn is alpha x1, alpha x2, alpha xn. Okay, as tuples. So two things that are in the same direction from the origin are the same. Okay, so in fact in algebraic geometry especially, so remark, we denote, actually you usually will take the different notations. So like, might as well give the nicer notation. Generally Rpn is equal to Rn plus 1 by tilde, where Rn plus 1 is going to be denoted as x0 to xn. So we have an extra coordinate xi in R. This is just a change of notation, and equivalence classes are denoted x0 colon x1 colon all the way to xn. Okay, so what we have here, and we can, so we also have versions Cpn minus 1, etc. So let's see a couple of facts about Rpn. Firstly, note each element x1 xn is equivalent. So let's say x0 to xn in Rn plus 1 is equivalent to, well, exactly 2 norm 1 elements. So, and if one of them is v, whatever x hat, the other is minus x hat. Hence, there is another description of Rpn minus 1. So Rpn is actually Sn by vector notation. Let me suggest u is equivalent to minus u. Okay. So to show these two spaces are equivalent, you just construct continuous maps in either direction and observe their bijections. I mean, observe their inverses of each other. So the continuous map is constructed by simply looking. So hence, like might as well have a quick proof. Rpn is by definition. So you're defined. So sketch of proof. Define Rpn. So we'll define in one direction. So we define Rn plus 1 to Sn by u is equivalent to minus u by x maps to the equivalence class of x by norm x. Of course, this is not well defined, but I don't want it to be. So Rn plus 1 minus the origin is mapped to this and induces. Well, if two things differ by scaling, they're up to norm, they're the same. So it induces Rpn to Sn by u tilde minus u tilde. And the other way, also define Sn into Rpn. Okay, given by this, how do I do it? As the composition. Sn is of course the sphere. Sn is included into Rn plus 1. And we have a quotient map to Rpn. Okay, and then we are done. So we have this, and then this induces. Well, you see that if two things are negatives of each other, they give you the same image here. Induces the map from Sn by u is equivalent to minus u to Rpn. And these maps are inverses. So this was an example of working with quotients, undoubtedly a bit sketchy, but nothing is difficult in what is left. So all you have to do is at set level have construct well-defined functions. They are automatically continuous. Okay, so let's look at one more aspect of it, which is what Cayley was motivated by. And again, I will be sketchy, which is that we can actually embed an affine plane into the projective plane. Okay, and which has a sort of well-defined image. Namely, we embed Rn into Rpn by, let's x1 xn maps. So let's use our notation now. The 0th coordinate we'll call 1 and map all these to xn. Okay, so this has image. Well, we can identify it naturally with Rpn minus 1 dimension lower, because the points that are not in the image are those with 0. If we just drop that 0, that coordinate, we have this kind of identification. And on this, on the image, can define a continuous map. What is on the image? We can define a continuous map. Okay, so in fact, I could write this more clearly, which is the image. The image in Rpn of x0 xn in Rn plus 1 such that x0 is not 0. Okay, so you look at those where the first coordinate is not 0, so we can define a continuous map by, on the image we can define a continuous map by Rn minus, rather let's give this a name of let's just call it Rn plus 1 positive or something. So define the map Rn plus 1 positive to Rp, not to Rn, by, if I have x0, xn, I just divide everything by x0, x1 by x0, xn by x0. Okay, and this induces a continuous map. And which is the inverse of the above? Which is the inverse? An inverse I was going to say, but inverse is unique, of looking at x1, xn, it maps to 1 comma x1, x2, so on xn. So there's a natural inclusion. This was Cayley's trick inclusion, except that I've put the coordinate in the first instead of the last, the extra 1 padding coordinate. So you include things by putting 1 and then taking these. This is not a surjection even up to scaling, because you miss those where the first coordinate is 0. Okay, but if we exclude that on the image of this set, which is we exclude those where it's 0, we can divide by the first coordinate and construct a map in the other direction. And if two things are proportional, equal up to scaling, they'll have the same image. So we do have a well-defined map. And it's easy to see they're inverses of each other. One way it's almost trivial. If we divide everything by 1, we get what we wanted. But conversely, if I look at x1 by x0, xn by x0, and then include, I would get 1 comma x1 by x0, so on xn by x0, but that is equivalent to x1 to xn 0. Okay, so this is equivalent, which is the inverse of these map, not as a map to Rn, but as a map to Rpn. This map. So I should have written this a little bit better. So it's important in this case, instead of saying images, remembering the image. So we are looking at the equivalence classes, not these. So we have a map which includes this. Actually, even here should rather say 1 colon x1 colon xn. So this is the equivalence class of this. So we embed it by mapping to the equivalence class of these proportionately. This has an inverse on the image, and this is a continuous map. So these two give you an embedding. Okay, so this is an important example. It's also given us some hands-on working with topological spaces via quotients. And now here the quotients were very nice, but we'll see in an example that quotients can be quite horrible. They will not even be Hausdorff. And then surprisingly, sometimes non-Hausdorff quotients are still good things to work with, and we just see one example of that.